This is my Calculus 1 course. Today we're going to introduce integral calculus. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So far in this course, we have been covering differential calculus. And that's where we try to find the slope of a line that is tangent to the graph of a function. In the second half of this course, we're going to learn something called integral calculus, which is where we find the area under the graph of a function, that shaded yellow area there, specifically the area between the graph of the function and the x-axis. Now, Isaac Newton discovered in the 1600s that these two problems actually have an inverse relationship, meaning one is the opposite of the other. It's the opposite operation. And we're going to learn how that relationship works later on in the course. Now, area is measured in square units. Square centimeters, square inches, square miles. What you try to do is draw a bunch of squares and then figure out how many squares can fit in a region, and that tells you what the area is. The problem is, with this graph, we have a curve, and squares have sharp corners to them. Now, we can measure the area of a rectangle really easily. We just take the width, say the width is 2 and the length is 5. Then we can just count the number of squares, and then we have the area. So we can find the area of rectangles. So what mathematicians do is they try to estimate the area under the curve by using rectangles, but that's just an estimate. We have these spaces in here which are going to result in an underestimation of the area under the curve. But what we can do is we can double the number of rectangles, as you see at the right. And if we double the number of rectangles, then the space in here, which is not being counted, that space is actually being reduced. It's decreasing. What if we double the number of rectangles again? We still have space, regions that are not being counted as part of the area under the curve, but those regions are getting smaller and smaller and smaller. So as you keep increasing the number of rectangles under this curve and calculating the sum of the areas of the rectangles, what you find is that sum approaches a number. And whatever number the sum approaches, that number is considered to be the exact area, this area that we're looking for under the curve. And the number that the sum of the areas of the rectangles approaches, that number is considered to be a limit, because the sum of the areas of the rectangles cannot go past that number. It just keeps getting closer and closer and closer to the number. That's why we call it a limit. So if A is the sum of the areas of all the rectangles, then the limit of A as the number of rectangles approaches infinity, again, that's considered to be the area of the region between the graph of the function and the x-axis. That's this area up here, the exact area. So isn't that interesting that we're using limits when it comes to this problem in integral calculus? We use limits when we learn differential calculus, but now we're using limits in integral calculus. That's very interesting. Again, we learned that differential calculus and integral calculus have an inverse relation, so it would make sense that there are some tools that we use in both branches of calculus. So again, the limit of the sum of the areas of the rectangles as the number of the rectangles approaches infinity is the exact area. Now notice we say the number of rectangles approaches infinity. All that means is that we're just adding more and more rectangles. So what if we get 1 trillion rectangles? That means the number of rectangles is getting really, really big. It's approaching infinity. But the limit of the sum of the areas of the rectangles, that limit represents, again, the area under the curve. So that is integral calculus. As you can see, it's not really that difficult of a concept to understand. In my opinion, understanding differential calculus is actually more difficult. Now, mathematicians suspected that these two problems had an inverse relationship before Isaac Newton even proved that they do. And let me show you a little bit about why they suspected. If we wanted to find the slope of this red line, and let's say we had 2 points on the line, the purple and the blue point, we could use this formula to find the slope of the line. And again, that's differential calculus. That's the derivative, is the slope of that red line. Now, we're going to talk about this notation here. We call that delta y. That just means change in y. And delta x means change in x. Delta is a Greek letter that means change in mathematics. Again, we'll talk more about that later. Now, if you want to find the area of a rectangle, if we call the length of the rectangle delta y and the width delta x, then the area would be delta y times delta x. And again, change means, if you find the difference, that's change. So let's say today you have $100 in your bank account, and then tomorrow you have $150 in your bank account. To find the change, you subtract, just like we're doing here. 150 minus 100 is 50. So look at the difference here. We have division and we have multiplication, but division and multiplication are opposite operations or inverse operations. So that's why mathematicians suspected that there's a relationship between these two problems, and again, it turns out that there is. Now, before we go into finding the exact area under a graph using those principles that we just discussed, we need to learn something called Riemann sums. A Riemann sum is just a sum of all the areas of rectangles under a curve. So it's what we just did. But the reason we call it a Riemann sum is because the height of the rectangles, you could call them the lengths, and by the way, normally we say that this length here, that dimension is the length, and this dimension is the width, right? And we say the area is length times width. But for our purposes, it's probably going to be better to call the length the height of the rectangle. So the area of each rectangle is going to be the height times the width, but it's the same thing. It's the same formula. So a Riemann sum uses this point, for example, this green point, to calculate the height of the rectangle. We need the height and we need the width. You see this green width down here? We need that green width, and we need this blue height. You see that blue height there? We need the green width and we need the blue height. So Riemann sums, they use that green point up there to calculate the blue height of the rectangle. So this point is xy, right? We'll just call it xy. The y value of this point is the height of this rectangle. And the y value of this point over here is the height of the second rectangle, this rectangle here. And the y value of this point over here, that's the height of this rectangle. And the reason for that is because notice that the left corner of each rectangle is touching the red graph. The left corner of each rectangle is touching the graph. So that's why it's called a Riemann sum, is because we're using the function to find the heights of the rectangles. And so this is a way for us to use the function. This is the function up here. We're using the function and we're using rectangles to estimate the area under the curve from A to B. In this case, A is -2 and B is 3. So let me show you the region that we're trying to find the area of. So it's this region here. So you notice that some of those rectangles are going to tend to give us an overestimate because they're going over this blue area. So all this blue area in here. This is the area that we're trying to estimate. That's the goal. All right, now some rectangles are going to tend to give us an underestimate. That's these, because they're actually below the curve. So let's try this example. It says here, estimate the area under the graph of f of x equals -1/4 x squared plus 4. That's this function here. From x equals -2 to x equals 3. So that's the bounds, the horizontal bounds. And they want us to use a Riemann sum calculated with 5 rectangles. Notice that there's 5 rectangles down there. And they want those rectangles positioned at left endpoints. Left endpoints. What does that mean? Well, it means that the left corner of each one of these rectangles, as we talked about before, is touching the red graph. Do you see that? Each left corner, each upper left corner of each rectangle is touching the red graph. Now look at the right. The green circles are the right upper corners of the rectangles. They don't touch the red graph, right? Again, that's why using these rectangles, it's said that we're using left endpoints. Left endpoints because it's the upper left corner of the rectangle that's touching the graph. So as you can see, this is really not a difficult concept that we're doing here. What students really have trouble with is the function notation. Okay, so let's do these calculations. Now I've already written all this stuff down for you because it would take too long to watch me write all this stuff. But when you do one of these problems, you're going to have to write this down. We have to find the area of all of these rectangles. So we need to figure out what the width of each rectangle is. You see these black circles down here? Those are the widths. Now you can see that the width of each rectangle is 1. Now it's not true with Riemann sums that the widths of the rectangles have to be the same for every problem that you do. But in all the problems that we're going to do today, the widths are going to be the same because those are the most common problems that you'll see. But on the advanced placement test, you'll see rectangles where the widths are not the same, but that's okay. We'll do some of those problems later on in the course. I don't want to confuse things right now. We'll just do the most common problems. So you see down here we wrote the width of each rectangle is 1. We can see that just by looking at the graph in this particular case. So what we're going to do is we're going to calculate the area of the first rectangle, the area of the second rectangle, third, fourth, fifth, and add them up. We're adding the areas. And that's going to be an estimate of that area that I showed you with the blue, where I shaded the blue. And again, area of a rectangle is height times width, or length times width, however you want to think about it. But, as I mentioned, the orange height, the green height, the purple height, the yellow height, and the pink height, they are found by discovering the y values of the graph, the y values of these points, these what we call endpoints. So this is where students get a little confused. F of negative 2 is the y value of that point up here, that point that I was talking about. F of negative 2 is the y value of that point. Now, of course, the width is 1. We talked about that. So there you go. This is the area of the first rectangle, but we have to calculate the orange expression. And the same is true with, then we plug in, or we find that the heights of the triangles using the function again and again. We have 5 rectangles. So why does it say negative 2? What does a negative 2 mean? This is where students have trouble. Well, what this means is you have to plug in x equals negative 2 to the function, and then the output is equal to the height of the rectangle. All right, so in calculus we would say that that point is x comma f of x. In function notation, that's f comma f of x. F of x is the y value. So in order to find that y value, you have to plug in negative 2. So in this case it would be negative 2 comma f of negative 2. So the x value of that point is negative 2. The y value of the point is f of negative 2. And that's what really confuses students. So I'm going to write it out here because I can't fit it there. It's just function notation. I know it's very confusing. Probably one of the biggest problems that students have when they take their first calculus course is function notation. When you're done with this course, you're going to have function notation mastered, or mostly mastered. So again, that yellow value, that's the height of the rectangle. That's the y value. Now, you don't have to use that notation. You don't have to use f of negative 2. I'm just showing you that just so you can know that the outputs of the function are the heights of the rectangles. So how do we find f of negative 2? Well, we go up to our function here and we plug in negative 2. Again, we count out 1, 2 in the negative direction, so the x value for this corresponding point here is negative 2. Then we plug in that x value to our function, and the output is this value here, this height. So the input of the function is negative 2. That tells us where to go. We plug that negative 2 in to this function, and whatever we get, that's the height of this rectangle. Then we plug in negative 1 to the function and calculate, and that gives us the height of this second rectangle. Then we plug in 0. You see this next endpoint is at 0. Plug in 0 to this function, and whatever we get, that's the height of this rectangle, and so on and so forth. So notice that we did that. We plugged in negative 2 in the orange expression. That's the function. We plugged in negative 1 in the green expression, 0 in the purple expression. And I know it might be kind of hard to see this, but I'm going to try to keep that graph in the window. And we plugged in 1 in the yellow expression and 2 in the pink expression. So again, the orange, green, purple, yellow, and pink, those are the heights of the rectangles. And the light orange color is the width. The width is the same for all of them. So now we multiply them, or first we calculate the orange as 3, and the green is 3 3/4, the purple is 4, the yellow is 3 3/4, the pink is 3, and I just kept the light orange width of each rectangle so you know what exactly is happening. So then we multiply, we get 3, 3 3/4, 4, 3 3/4, and 3, and then we just add those numbers together. So it's very important to understand that each one of these numbers, 3, 3 3/4, 4, 3 3/4, and 3, they represent the area of one of those rectangles. So this is the area of the leftmost rectangle, this is the area of the next rectangle, and so on and so forth. So again, there's 5 rectangles, so we have 5 numbers. Add them all up and we get 17 1/2. And that's an estimate for the area under the curve. Now again, I don't mean to sound like a broken record, but I want you to be completely aware of what we're trying to do. We're trying to estimate the area that you see here, this blue area. And we're using those triangles to estimate this blue area. That's the whole point of this. We want to find the blue area, which is the area under the curve, but above the x-axis. It's between the red curve and the x-axis. So that's it. We're done with that problem. So it's really not difficult. It's just that students need to get used to how the outputs of the function give us the height of the rectangles. If you understand the basic principle there, then the rest of these problems are going to be easy. At least the problems on Riemann sums. Now, let's do the exact same problem again. But this time, let's use right endpoints. Instead of using left endpoints, let's use right endpoints. What does that mean? Well, in the previous problem, again, we called these left endpoints because the top left corner of the rectangle hit the graph, right? But in this problem, the top right corner of the rectangle is going to hit the red graph. The top left corner of each rectangle, that's not going to necessarily hit the red graph. You see those green circles? Those corners, those top left corners are not hitting the graph anymore. So we call this a Riemann sum calculated using right endpoints. So now we're going to do the same thing. The width of each rectangle is obviously still 1, right? These widths are just 1. And we have to calculate the heights of each triangle, or excuse me, the heights of each rectangle. And so we're going to do the same thing we did before, except instead of starting with the output given an input of -2, we're going to start by plugging in x equals -1, because this point here, rather than this green point, the black point gives us the height of the first rectangle. The green point does not. That's very important, because the green point is not at the corner of the rectangle. So we have to start at x equals -1. We have to count out -1, and then we're going to plug in -1 to the function, and whatever we get, that's going to be this green height. Excuse me, it should go to here. It's going to go all the way up to the graph. Then we're going to plug in 0 to find this height. Plug in 0 to this function to find that height. Then we're going to plug in 1 to the function to find this height. Then we're going to plug in 2 to the function to find this height. and so on and so forth. So we're actually finding the same values. We just shifted the values over. We got rid of this value here, or this number, but we added another number at the end. That's this f of 3 times 1, because now we have to plug in 3 to find the height of this rectangle. We didn't do that before. We just plugged in 2. So we plug in our numbers into the function, and we calculate, and we get our area here of the first rectangle. This is the area of the second, area of the third rectangle, area of the fourth rectangle, and so on and so forth. Now, there's something I forgot to mention. In the previous problem, we had this thing that said L5. Why did I write L5? Well, because we're using left endpoints, and we're estimating the area with 5 rectangles. But down here, we don't have L5, we have R5, because we're using right endpoints, rectangles calculated at right endpoints. So we add our numbers and we get 16 and 1/4. So 16 and 1/4 is close to what we got in the previous problem. We got 17 and a half, if I remember correctly. Yeah, we got 17 and a half if we use left endpoints. And if we use right endpoints, we get 16 and 1/4. So there's a difference. Now, this triangle symbol is a Greek letter that is used in mathematics to indicate change. The letter is called delta in the Greek alphabet. And in calculus, this symbol here, delta x, is often used to notate the width of a rectangle. It means change in. Or you can say it's the difference between two x values. Now, if the widths of rectangles in a Riemann sum are equal, they actually don't have to be equal. But all the problems that we're going to do today, they're equal. If the widths of the rectangles in the Riemann sum are equal, then the following formula can be used to calculate the width of each rectangle, where B and A are the right and left bounds of the area being calculated, as you see down here. And N is the number of rectangles used for the approximation. So you don't have to use this formula, but sometimes it's very convenient to do that. In this example, we didn't really need a formula because the widths were pretty easy to calculate. We could see that the width of each rectangle was just 1 by looking at the grid. But in some cases, it's not exactly obvious what the width of each rectangle will be, so this formula is useful. So we just take this number here and subtract this number, and then divide by how many rectangles there are, and that's a surefire way to give you the width of each rectangle in a Riemann sum, assuming that the widths are equal. And in most cases they are. Okay. So here is the expression for a Riemann sum. F of x subscript I is the height of each rectangle. Delta x is the width of each rectangle, and n is the number of rectangles used for the corresponding approximation. Now you're probably wondering, why do we have a subscript I there? Well, that's because x subscript I depends on what type of Riemann sum we're using. We could use a sum with left endpoints or right endpoints, and we're going to learn later on in this course that we could be using Riemann sums with midpoints, what we call midpoints. So that's why we write x subscript I. It's kind of ambiguous what that really means. But again, the most important thing to understand is that blue expression is the height of each rectangle, and the orange expression is the width of each rectangle, and we're multiplying the width and the height to get the area of each rectangle. Remember, length times width or height times width is the area of each rectangle, and we need sigma notation to show that we're adding the areas up. And we'll use sigma notation more later on in this class. So let's do some practice problems. It says here, estimate the area under the graph of f of x equal to sine x from x equals pi over 6 to x equals pi over 2. So those are the horizontal bounds. And it tells us to use a Riemann sum calculated with 4 rectangles. So you can see in the picture we have 4 rectangles. I'm giving you a picture to help you because you're just starting out with these concepts. And the rectangles are positioned at left endpoints. What that means, again, is that the upper left corner of each rectangle is touching the graph. So we are going to estimate this area. We're estimating this area using those rectangles. So we need to add up the areas of the rectangles. So the area of a rectangle is height times width. So we need to find the widths of the rectangles first. And again, for all the problems today, the widths of the rectangles are going to be the same widths. They all have the same widths. Now, in the previous problem, it was easy to see what the width of each rectangle was. It was just 1, right? So we didn't need to really worry about that calculation. But here, it's not exactly obvious what the width of each rectangle would be. Now, if I allowed you to figure that out for yourself, you could probably do it. In fact, you could probably figure out what the sum of the areas of these rectangles are on your own. So we can estimate that area under the curve from pi over 6 to pi over 2. But if you want a fast way to find the width of each rectangle, you can again use this formula. So B is always the right endpoint, or the right bound, and A is always the left bound. And then you divide by the number of rectangles, which is 4. Now here we have a complex fraction. That's pi over 3 divided by 4. And when you're dividing, remember you flip the divisor, so you have pi over 3 times 1/4, and we get pi over 12. So each one of these rectangles has a width equal to pi over 12. So we're calling the area L4. There's 4 rectangles, and we're using left endpoints. So you see we have our pale orange widths that we're multiplying. But the problem is, how do we find the yellow, blue, green, and pink heights? How do we find the heights of the rectangles? This is the part where students have a little trouble understanding. So we want to find this length here, that blue length. That's the height of the first rectangle, right? So how do we find that height? Well, notice that the height is just going to be the y value of this point here. So how do we find the y value of that point? Well, we first have to figure out the x value of the point, and then we plug it into the function, and whatever sine of that x value is, that's the y value, the height of the rectangle. So what is that x value? Well, we just count out. It's going to be pi over 6. We know the x value, they tell us right here. So you just plug in pi over 6 to your function, and that gives you the y value of that point, which is the height of the rectangle. That's the part that students have a little trouble understanding. So the height of the first rectangle is sine pi over 6. We plugged in pi over 6 to the function. Then we multiply by the height by the width. Okay, so now let's find the height of the second rectangle. That's this length here. We have to find the x value of this point, plug it in, and then that'll give us the y value of the point, which is the height of the rectangle. So what we have to do is we have to count out pi over 6 and then add a width, add pi over 12, because that's the width of that rectangle, right? So count out pi over 6 and then plus pi over 12, and that gives us the x value of that point. So pi over 6 plus pi over 12 is pi over 4. So then we plug in pi over 4 to the function, which is the sine function, and that is the height of that second rectangle, this rectangle here. Then we multiply it by the width, and we have the area of the first rectangle. So now we do the same thing for the third rectangle. And if you have the idea here, you can just go forward. You don't need to listen to all this. But we have to find the x value of that point. So we count out pi over 6, then we add pi over 12, then we add another pi over 12, and that gets us to the x value of that point. We plug it into the function, and we've got the height. So we added pi over 12 twice. Notice that we're adding the width over and over and over again of the rectangles. Then we just add the width again to get to the x value of the next point, and plug it into the function. That gives us our pink height, and then we just multiply the height by the width, and so on and so forth. So we have the area of the first rectangle, the area of the second rectangle, the area of the third rectangle, and the area of the fourth rectangle. And of course we can just add those fractions by getting a common denominator. And now these are special angles: pi over 3, pi over 6, and pi over 4. Pi over 6 is 30 degrees, pi over 4 is 45, pi over 3 is 60 degrees. Now, we learned in my trigonometry course that we have special angles. Pi over 6 is 30 degrees. How do I know that? Well, pi is 180 degrees. That's one way to do it. The surefire way to do it is to multiply by the conversion factor. Remember, we learned the conversion factor. There's 180 degrees and 1 pi radians. So the pi's cancel out, you're left with 30 degrees. If you wanted to go in the opposite direction, you started with 30 degrees, you'd multiply by the same conversion factor, but now it would be flipped. And again, you get back to pi over 6. So this conversion factor can be used whenever you're converting, or in these cases you can just change pi to 180 degrees and just simplify the fraction. You can go back to my trigonometry course if you'd like more review on that, but the reason that we learned trigonometry before doing this stuff is we don't really have a lot of time to go into the specifics of that. Now, pi over 6 is 30, so that means we have a 30, 60, 90 degree triangle. This side is x, this side is 2x, and this side is x root 3. That you should have that memorized. If you don't, you can type in special triangles, and there's also the 45, 45, 90 degree triangle, which we're going to need because we have pi over 4. So we have x and x root 2. So these triangles you should have memorized. So very important to understand, this is not a trigonometry course, this is a calculus course, so you need to know this. I think I reviewed this at the beginning of my course. And so sine pi over 6, that's sine 30. So sine 30 is equal to opposite over hypotenuse, which reduces to 1/2. So that's where we got 1/2 here. Now, if you don't want to use all that stuff, you can just plug that into your calculator. but you really should know how to find those values without a calculator. The only value you cannot find is the pink value, because 5 pi over 12 is not a special angle. So you're going to need a calculator for all this, and we should come up with this estimate for the sum of the areas of the rectangles. And again, that's an underestimate of the area under the curve, because you can see that the rectangles are below the curve. Okay, so now we're going to go on to another problem. So again, the whole point of this was to find the sum of the areas of those rectangles. This problem is exactly the same as the problem we just did. No difference whatsoever. Except we have right endpoints. So notice that the top right corner of each rectangle is actually touching the red graph. That's what it means to use right endpoints. So now we're just going to find the sum of the areas of these rectangles. We have the same widths because it's the A and B are the same for these. And I'm going to go ahead and write that formula. I didn't write that formula here. So we have B minus A over N. That's our formula, right? A and B are the same. We're still using the same number of rectangles, so we have the same width. And so we're going to find the height of this triangle first, but we can't use this side. We want to use this side because we're using right endpoints. So we need to use the y value of this point, that blue point there. So what we need to do is we need to find the x value of that point and plug it in to this function. So we're going to count out pi over 6 and then add a pi over 12, and that's the x value. So pi over 6 plus pi over 12. So the difference is we kind of moved over one x value. Instead of starting with pi over 6, we're starting with pi over 6 plus 12. So we're kind of shifted over a little bit. And we're going to keep finding those heights as we move this point over. We're going to find the y value of that point. That's the height of the second rectangle. And then we're going to find the y value of this point, which is the height of the third rectangle. And then we're going to find the y value of this point. In order to find the y value of that point, you just have to plug in pi over 2 into the function, because the x value is pi over 2. So plug that in. Sine pi over 2 is the height of the last rectangle. Okay, so here's your numbers. We have the same expressions. The only difference is we're missing this expression that we started with on the previous problem, and we have an extra expression over here at the right. So we do the math and we end up with R4 is 0.9265. So that was bigger than the number we had before, because these rectangles, they're an overestimate of the area because the rectangles are above the curve. And again, it's R4 because we're using right endpoints, and 4 means 4 rectangles. So let's look at a couple more of these problems before you try one on your own. Here we have a totally different graph. We have an exponential function. So it says estimate the area under the graph of f of x is equal to 2 to the x power from x equals -1 to x equals 2. So those are the horizontal bounds. And we're supposed to use a Riemann sum calculated with 6 rectangles. Notice in the picture we have 6 rectangles, and they're positioned at left endpoints, meaning the top left corners of the rectangles are hitting the graph. So we need to use those blue points to find the heights of the rectangles. So let's find the width of each rectangle. We can use this formula. So we have b, this number, the right bound, minus a, this number, the left bound, and we get 1/2 for the width of each rectangle. You can probably see by looking at the picture that the widths are 1/2, but you can also use that formula. So we just do the same thing that we did before. And I want to make it clear that you don't have to write any of this, and you don't have to write this step here. Don't worry about that. All you have to do is just understand, how to find the heights, and just start at this step here. So the height of the first rectangle, the farthest left rectangle, is 2 to the negative 1 power. So do you see what that is? The height of the first rectangle, that small rectangle, is 2 to the negative 1 power. Okay, again, because we need to use this point, that blue point, the y value of the blue point, which is the output of this function, that's the height of that rectangle. How do you find the output? Well, you have to plug in the x value. What is the x value? It's -1. Plug in -1 here, and that gives you the height of this first little rectangle, that blue distance there. Alright, then you plug in -1/2 to the function, and that gives you the height of the next rectangle. Then you plug in 0. That gives you the height of the next rectangle. So I'll move this along as we do this. So you plug in -1/2. That gives you the height of the next rectangle. Plug in 0 into this function up here. That gives you the height of the next rectangle. Plug in 1/2. That gives you the height of the next rectangle. Plug in 1. That gives you the height of the next rectangle. Plug in 1 and 1/2. That gives you the height of the next rectangle. Again, we're plugging into this function. So that's how that works. So we plugged in -1, -1/2, 0, 1/2, 1, and 1.5. And of course, those are the heights. Then we multiply by the pale orange widths. So we have the area of the first rectangle, second rectangle, third, fourth, fifth, sixth. Now, students often are pretty rusty when it comes to negative powers and fraction powers, but you can go back to my intermediate algebra course and review that if you want in the exponents classes. But remember, negative powers just go down into fractions, and fraction powers become square roots, or some sort of root. It doesn't necessarily have to be a square root. 0 powers are always 1. And again, this is all stuff that you just need to know. This is exponent rule number 10 here, and so on and so forth. So we combine, and you can use a calculator for this stuff. Our estimate is 4.22487. So that's the area, or the sum of the areas of all those rectangles. Okay, so again, these are called Riemann sums. So now we're going to do the exact same thing that we did before, no difference whatsoever, except we're going to use right endpoints. So now we have to use the top right corner of each one of these rectangles. And again, what we're trying to do is we're trying to estimate this area. This area here. And obviously this is going to be an overestimate because the rectangles are above the red curve. We just want to figure out the area below the curve and between the curve and the x-axis. So we just need to know what x values to plug into our function to find the heights of each rectangle. Now, in the previous problem, we started by plugging in -1 to the function, and that gave us the height of the first rectangle, but we're going to start by plugging in -1/2. We have to count out -1/2, and that's going to give us the height of this rectangle when we plug it into the function. Or excuse me, the height of the first rectangle. So that's the difference. We're starting with -1/2 rather than -1. Also, when we get to the far right, we're going to plug in 2 to the function to find this height. X equals 2. So we have 2 squared times the width, and add up all those areas, and we have 5.97487. So I want you to get a picture of this information here, and that'll help you. And get a picture of this information here, and these problems that we did. Okay, so I want you to try number 5. So you're going to start out by finding the width of each rectangle, and you can use this formula here. Now remember, B is the right bound, and A is the left bound, and N is the number of rectangles. So go ahead and try that problem, and if you get stuck, that's okay, but give an honest attempt, and when you come back, we'll do it together. Okay, we're back. So if you got that answer, good. So I want you to take a picture of these two problems here and use them to help you do number 6. Number 6 is the exact same problem, except now we're using right endpoints. So remember, you need to use your formula. B minus A over N is equal to the width of each rectangle. So go and attempt number 6. B is 4 and A is 1. When you come back, we'll do it together. Alright, we're back. So if you got that answer, good. Okay. I want you to try number 7. And for number 7, notice that we're supposed to use 4 rectangles, but because of the nature of this graph, one of the rectangles is actually going to be non-existent. But we're still going to use 4 for n. So try number 7, and when you come back, we'll do it together. Okay, we're back, and we get 6. That actually turns out to be an exact value, not an exact value of the area under the curve, but an exact value for the estimate. So if you got that right, very good. Again, notice that one of the areas was 0 because there's no rectangle there. So get a picture of problem number 7 and number 6. And I want you to use those problems to try this one. This is the same problem that we did previously, except now we're using right endpoints. So try this problem. When you come back, we'll do it together. Okay, we're back. And R4 is going to be, looks like 6. So that was a rare case where the calculation with the left endpoints is the same as the calculation with the right endpoints. Okay, that probably has something to do with the fact that the graph is symmetric about the y-axis. So if you got that right, excellent. So now we're going to learn how to write these sums using sigma notation. So we're going to write Riemann sums using sigma notation. Now this is the part of the class where things can get pretty intimidating for students, because you can see that this notation here is very, very intimidating for students. It's important to understand that this expression here is the height of each rectangle, and this expression is the width. Alright? And this expression is the height of each rectangle, and this is the width of each rectangle if we're using right endpoints as opposed to left on the other formula. So these are the expressions that you're going to need to use to find the estimation that we're looking for. So what is A? Well, A is the left bound and B is the right bound. You see that in the picture at the right here, those pink letters. And what we're trying to estimate is this area here. We're not going to find the exact area, but we're going to estimate that area with n rectangles. In fact, I'm going to actually show that. So I'm going to add this part here just so we know what these expressions mean. So this may seem kind of intimidating to you to use this notation, but over time you'll see what it means. Again, one of the biggest goals for you in this course is to learn function notation, or get a better understanding of function notation. So now the most difficult thing to understand is what this expression is. That is the input of the function. Why do we write a plus b minus a over n times I? And over here, why do we write a plus b minus a over n times I minus 1? It's not exactly obvious. Again, your understanding of functions is probably not going to, it's not going to be complete until you get to, until you get through this course. When you finish this course, that's when you're really going to understand function notation. But right now, we'll just use the formula, and over time you'll start to it'll start to become apparent to you what that really means. It says down here, write the sums in problem numbers 1 through 8 using sigma notation. Graphs are provided for reference. So this is from problem number 1. We're going to write the sum of the areas of these rectangles in sigma notation. So we already found the sum, but we just want to write it using sigma notation. Now notice that the upper left corners of the rectangles are touching the graph. That means we're going to use the formula that employs left endpoints, this formula here. So I'm going to go ahead and copy that down. Or copy it and bring it down. My computer's going kind of slow here. So there's the formula that we're going to use. And so all we have to do is just start plugging things in. So we're using 4 rectangles. A is the left bound, pi over 6. B is the right bound. And again, we're using 4 rectangles. And whoops, I forgot my I minus 1. And again, we have pi over 2 minus pi over 6 over 4. So this is the width of each rectangle. I know it doesn't seem like it, but that's the width. Remember, we talked about that. And this here is the height of each rectangle. So these numbers here, those were n, and these numbers are a, and these numbers are b. Of course, you don't really have to use colors here. I just want you to see where these numbers are coming from. Alright, so now we just have to simplify the formula, and eventually we're going to replace f with what the actual function is. In this case, it's the sine function. So we simplified and we got pi over 12. We don't really need to do that again. Remember, that was the width of each rectangle in problem number 1. So I'm going to distribute. We have pi over 12 times I minus pi over 12. And pi over 6 minus pi over 12 is pi over 12. So that's about as far as we can go, unless we change f into the actual function that we're using. So what is f of pi over 12 plus pi over 12i? Well, that's equal to sine pi over 12 plus pi over 12i. So all of this, well, I guess I'll use that color for the width. We've been doing that so far, and I guess I can use maybe pale blue for the height of each rectangle. So that became that. And that's it. Now, if we want to we could actually take this pi over 12 out and put it in front, but it's not really necessary. So that's the answer we're looking for. We have the sum using sigma notation. So in order to prove that this is correct, we can do two things. We can just start plugging in values for I, and you can see why this formula works. So let's plug in, we're starting with 1, so we plug in 1, right? If you plug in 1, you can do the math, but you get sine pi over 6 times pi over 12. That's the area of the first rectangle. This is the height of the first rectangle, and this, of course, is the width of the rectangle. So you multiply them, height times width, and you've got the area of the first rectangle. So then you plugged in 1 for I, right? Well, now of course you go up to 2, so you plug in 2, and if you do that, then you get sine pi over 4 times pi over 12. And this is actually the area of the second rectangle. Now, the reason that you add multiples of pi over 12 is because you're moving over. Your first x value was this x value. It brought you out this far. That's pi over 6. But then you're going to add a multiple of pi over 12 to get to here. And that'll give you the height of that rectangle. But then you add another pi over 12, and you just keep adding pi over 12s to get to the next x value you need to plug in to find the the height of the rectangle, and so that's why that works. You're always adding multiples of the widths of the rectangle. So I know that's pretty confusing, but that's basically how this works. If you don't quite understand that, that's okay. Very few students do when they first see this. It takes a while, like I said, to get used to the function notation. But there's a way that we can check to make sure that we did this correctly. You can use your graphing calculator. Now, I'm using a TI-84 Plus, of course. If you're using a different calculator, you're going to have to figure that out for yourself. But I'm not even sure your calculator does this. This is only going to be graphing calculators that are most likely able to do this. So if you're using your TI-84 Plus, you can push the math button at the upper left or middle upper left. Then use the down arrow key to go all the way down to number 10, where it says summation. Press enter. And what you should see is something like this. Trying to make squares here. So it's a template. You can enter x for this variable. That's the x, t, theta, n button at the middle upper left. And for this purple number here, you just put 1. We're starting at 1, right? And then of course this yellow number here would be 4. But then you have to copy down all this stuff into there. And you have to make sure that you're in radian mode. So push the mode button and push the down arrow key and make sure that radian is highlighted, then the blue second button, and then the mode button again to quit out of that. So you can enter it all in. So again, push the math button down to number 10, enter, and then you can push the X button, X, T, theta, n button, then 1, then the up arrow key, 4, and then enter all that in. And if you get what we got for number 1, which is we got 0.7956 approximately. So if you get that number, that means that your sigma notation is correct. So that's just one way to check. Okay, so let's move on to the next problem. You may see problems like this on the advanced placement test. They're not going to be exactly like this, but you'll have time to study and figure out how to do these types of problems for the advanced placement test, but this is just introducing the concepts. Okay, so now we have right endpoints. So let's go to our formula, and we're going to copy and paste the formula for right endpoints. Okay. So this is going to be very similar, almost exactly the same as the other formula. We have pi over 6 for A, and we can just write pi over 12 because we've already done this. Pi over 12. The only difference is instead of I, you have, or instead of I minus 1, you have I. That's pretty much it. And so we're going to replace that with sine pi over 6 plus pi over 12i times pi over 12. There you go. That's it. And maybe I'll just plug in the numbers just so you can see what that looks like. but since we already did the left endpoint problem, it's not really necessary to show all the steps. I'm just showing that we did the same exact thing pretty much that we did before. Only difference with this formula is again that we have I instead of I minus 1. Okay, so there you go. Let's try another problem. So what you're doing is you're just taking this function f, which is sine x, and instead of x, you're plugging in whatever this expression is. And that expression ended up being, when you simplified it down, it got to pi over 6 plus pi over 12i. So this expression here is exactly the same as this expression. The only difference is we're actually identifying what f is. So this is the input of the function. Okay, let's try another one. So now notice that we again, we're going back to left endpoints because the upper left corner of the rectangle is touching the graph. So I'm just going to write out the formula for left endpoints so I don't have to go over there and cut and paste. So we have I minus 1. When you have left endpoints, you need I minus 1. So how many rectangles do we have? 1, 2, 3, 4, 5, 6. And if you want to, you can go ahead and, write 2 to whatever this is if you prefer to do things that way. So we have -1 is a, 2 minus -1 over 6 times I minus 1 times 2 minus -1 over 6. So a is -1 and b is 2. There's 6 rectangles. Okay, so let's simplify. It looks like we get 1/2. 2 plus 1 is 3. 3 over 6 is 1/2. And now we can distribute. So we have 1/2 I minus 1/2. And -1/2 plus -1, we can just write that as -3/2. Now again, you can just write 2 to all this if you want right off from the start. Let's get some more room. So now we're ready to replace f with the actual function. So what is the actual function? It is 2 to the x. So instead of f of this, we have 2 to this power. So we can use parentheses just to be clear what happened there. So this is your width, and this pale blue is the height. So the width of each rectangle is the orange, and the height is the blue. And I'm going to use a different color because that blue kind of looks weird against the blue lines. So there you go, that's the answer. Okay. So now we're going to do the same problem, except now we're using right endpoints. Notice that the right corner, the right upper corner of the of each rectangle is touching the graph. So I'm going to write the formula. It's the same formula we just wrote, no difference whatsoever, except instead of I minus 1, we just have I. So we have, again, 6 rectangles, and A is -1, and we have B is 2, so 2 minus -1 over 6 times I, and again 2 minus -1. So we're just kind of plugging in just to show that we know what we're doing with this formula. And now we change f to 2 to the x, but instead of 2 to the x, it's 2 to the -1 plus 1/2 I times 1/2. So that's the width of each rectangle, and this is the height of each rectangle. And that is our answer. So again, you can put this into your calculator. Again, press the math button, go down to number 10, enter it in, then press enter and see if you get the answer that we got for number 4. Okay, so now it's time for you to try. I want you to try number 13, but go ahead and get a screenshot of all this information here, and number 9, and I'll let you use numbers 10 through 12 to help you. So go ahead and try number 13. So you're writing the sum with sigma notation, and when you come back, we'll do it together. Okay, we're back. So if you got that answer, good. Okay, so I want you to get a screenshot of these 4 problems, and I want you to attempt number 14. Go ahead and try number 14. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, I want you to use number 14 to help you do number 15. Now, please be aware that one of these rectangles is a ghost. It's not there. But it's very important to understand that you still have to use 4 for n. If you use 3, then you're going to get the wrong answer. That's just the nature of that formula that we're using. So go ahead and try number 15, and when you come back, we'll do it together. All right, we're back. So if you got that answer, good. All right, so I want you to use numbers 14 and 15 to help you with number 16. Again, remember we have 4 rectangles, even though one of the rectangles is a ghost, so use 4 for n. Try number 16. When you come back, we'll do it together. Okay, we're back. So if you got that answer, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go and do that now. Here's screenshot number 1 and number 2 and number 3, 4, 5, 6, 7, 8, and don't forget to get your homework. Remember, the homework is not optional. If you don't do the homework, it's 100% guarantee you'll learn absolutely nothing in the entire course. So get a screenshot here, screenshot number 1, and screenshot number 2, and 3, 4, and 5. But don't go before you get the answers. It's not enough just to attempt the homework. It must be done correctly. So here's the answers. Complete that homework and make sure that it's neat and that it's correct. And I'll look forward to seeing you in the next class.